Not the only comet in our solar system right now with a sunward-facing tail, which many are stating that is the most bizarre characteristic that it has. Here we have comet R2 SWAN, so this is C 2025 R2 SWAN, and we see that it very clearly has a sunward-facing tail.
Two comets, opposite sides of Earth, both displaying the same rare phenomenon. Something unusual is happening in our solar system right now. Comet C 2025 R2 SWAN has just developed a sunward-facing tail, mirroring the behavior of the mysterious interstellar object 3I Atlas. This rare feature has astronomers taking a closer look at what's unfolding above us. Let's start with what we're observing. Comet R2 SWAN was first detected on September 12th during its closest approach to the Sun, at just 0.5 astronomical units. That's roughly half the distance between Earth and the Sun. The comet flew in close to the ecliptic plane, the same flat disk where most planets orbit. It has a characteristic greenish color, caused by diatomic carbon fluorescing in sunlight. But here's what caught attention. In the past 2 weeks, R2 SWAN has developed a distinct sunward-facing tail. That's a tail pointing toward the Sun, not away from it. Normal comet tails point away from the Sun, pushed by solar radiation and the solar wind. A sunward tail is rare and optically striking. Now, R2 SWAN isn't alone. The interstellar visitor 3I Atlas, currently moving toward Jupiter, has been displaying a similar sunward tail for weeks. It also shows a greenish hue and similar jet activity. Both comets reached perihelion around the same time. R2 SWAN on September 12th, 3I Atlas on October 29th. And now both are showing this unusual feature simultaneously. So why does a sunward-facing tail form? According to the Astronomer's Telegram, which professional astronomers use to share rapid updates, the answer lies in geometry and dust particle size. These so-called anti-tails are formed by larger dust particles. Unlike smaller particles that get pushed away by solar radiation, larger grains are less affected by that pressure. They lag behind and stay closer to the comet's orbital plane. When Earth crosses or approaches that orbital plane, and the viewing angle lines up just right, those dust particles appear to project toward the Sun. It's an optical effect, but a real structure. For R2 SWAN, early November images showed only a faint hint of this feature. By mid-November, the sunward plume had grown significantly. Multiple observatories and amateur astronomers have now confirmed it. The timing suggests two possibilities. One, our viewing geometry improved, making the structure visible. Two, the tail itself is growing, or both. What makes this especially notable is the parallel with 3I Atlas. Two unrelated objects showing the same rare behavior at the same time with similar colors and similar positions relative to Earth. Now, let's talk about position. When you plot the current trajectories of both comets, something visually striking emerges. 3I Atlas is on one side of Earth. R2 SWAN is on the other. Both are near the ecliptic plane. 3I Atlas is about 5 degrees off the ecliptic. R2 SWAN is only slightly more inclined. This places them in roughly symmetrical positions relative to our planet. In military terms, this would resemble a flanking maneuver. There is no evidence of intent here. This is almost certainly coincidental, but the geometry is compelling. It also highlights a gap in our detection capabilities. R2 SWAN wasn't spotted until it reached perihelion. It approached from near the Sun's direction, hidden in the glare. we missed the entire inbound phase. This isn't unprecedented. Many comets are discovered only after perihelion, especially those coming from sun-facing directions. But it underscores the need for better coverage, particularly infrared in space-based instruments that can monitor the sun's vicinity. Another comet, K1 Atlas, not to be confused with 3I Atlas, recently fragmented into 4 pieces. R2 SWAN also showed signs of fragmentation and a brightness outburst earlier this season. Fragmentation is common under thermal stress, but the timing has drawn attention. Orbital modeling suggests R2 SWAN has a period of roughly 784 years. It's not a newcomer. It last passed through the inner solar system in the Middle Ages. So what's driving these similarities? Some researchers suggest both comets are responding to the same solar conditions. Specific alignments of the heliospheric current sheet, magnetic field configurations, or enhanced solar wind activity could trigger similar outgassing patterns. Others propose that rare tail structures may cluster when observational geometry favors visibility across multiple objects at once. For those exploring plasma physics, 3I Atlas has been of particular interest. Its irregular jets and morphology have led to speculative frameworks, including the idea of plasma structures exhibiting quasi-lifelike behavior under electromagnetic influence. While such ideas remain outside mainstream consensus, the unpredictability of 3I Atlas continues to fuel alternative interpretations, especially as those features now echo in R2 SWAN. From a broader perspective, this situation raises questions about our solar neighborhood. The Sun exists within a region dense with stars. Alpha Centauri, Proxima Centauri, Sirius, and dozens of nearby red dwarfs likely host planets, many inhabitable zones. Statistically, the existence of life elsewhere is probable. Whether intelligent or microbial, the sheer scale of the galaxy makes Earth's isolation unlikely. Some have speculated about multi-dimensional interpretations, where hypothetical entities might interact with physical reality in ways we don't yet understand. While unsupported by observational evidence, it remains a topic of fascination at the intersection of astrophysics and theoretical physics. As observations continue, both comets will help refine our understanding of dust dynamics, solar wind interactions, and heliospheric conditions. Whether the similarities between 3I Atlas and R2 SWAN prove coincidental or reveal shared physical drivers, the current alignment serves as a reminder. Comets are not inert. They are active participants in a complex and dynamic solar environment. The simultaneous appearance of sunward-facing tails in 2 unrelated comets, each on opposite sides of Earth, following near-ecliptic trajectories and sharing similar colors, is noteworthy. Even within strict scientific frameworks, this convergence invites closer scrutiny. Late detections, abrupt fragmentation, and unusual photometric behavior may be common in cometary science, but when so many anomalies align at once, it's worth paying attention. The solar system still holds many surprises. As our observational tools improve and our detection networks expand, we'll continue uncovering objects and behaviors that challenge our models. For now, Comet R2 SWAN and 3I Atlas remind us that space is far from static. It's active, unpredictable, and full of phenomena we're only beginning to understand. That's the latest on this developing story. We'll continue monitoring both objects as they move through the solar system.